Okay, we'll want to find out what the area of all those distributive tiles is. What is the area? And how would you know that? To know the area, you've got to have some numbers. You would need to know the length of this, right? Length of this, length of that. And the width and so on. The area is found by length times width. So it's not 32, not 24, not 24 units, not 96, none of the above. There's E, 1 point per E. If I didn't have E, we'd have it wrong. So E, there's the answer. Let's move to the next page. You can read that. And this time I'm going through this with my wife because I noticed it helped a lot for her when it helped me a lot to have her learning it while I was teaching it. How old are you, Ria? This is my wife, Ria. Ria, say hi.
Hello.
How old are you?
I just turned 70 yesterday.
Oh, wow. Well, we better really get going here. Oops, the length of the large rectangle there is not 3. When I show this to a lot of students, they think from here to here is 1, from here to here. From here to here is 1, from here to here is 1, and then they think, oh, that's 3. We'll see why in a minute. Now, a little bit more on that in a minute. But anyway, for now, I can definitely tell you that it's obvious that from here to here is not 3 of these things.
No.
It's not 3 of those.
I can see that.
You can see that here, but back over here, we didn't really know that. So students tend to think, oh, okay, that's 1, so this must be 3. So there's that. Let's go on. Now, we have here what unit, inch, millimeter, mile, pound, arbitrary. Well, pound, inch, but it's arbitrary, and we'll see a little bit more what that means. I'll put in E there, got 1 point. Let's go to the next page.
May I ask a little question?
Yes. Yes.
What do you mean by arbitrary?
Arbitrary, it can be up to you as to what you want to use, what you think is easiest to use. Here it's going to explain that we want to use the small square. We could use the large square. And we want the small square to have a length of 1 and a width of 1. Now, why? Why would we use this small square rather than the big square to measure all the other tiles? Why reference the size of the other tiles here by the small square there? Well,
is it because the small one can fit into the others?
Yes, that's part of it. And it says, are there more tiles with a short width or more with a long width? We can see, what do we have most of? We have width. The width is short on most of these. There's a short width. Okay. Here, this big thing has a large width. Okay. I wouldn't want to use that one.
Right.
Because if we call it, well, we'll see. Okay. So yeah, there's the answer to short. That's A.
Definitely.
And then if the width of the large square was assigned 1, then the not square rectangle's width would be about what? And that would be A.
Yeah.
Right there, A. I think you can kind of think about that. Would it be easier to label the small square's length and width as 0.385 or 1? And it'll be B. A lot easier to use that 1. Because if you do that, then you just count, okay, there's 1 and 1 and 1. You don't have to say 0.385. That's a lot easier. Okay, let's go to the next page. Here's another argument. We can let you read that. And, I would hate to go, if I was doing all along here, I'd hate to go 0.385 plus 0.385 plus 0.385. Of course, you could count them all and multiply, but it's even easier is just having 1 for that length. 1, 1, 1. How many ones are there? Of course, we don't have to do that whole thing, but obviously this is not going to be 3 right there, along there.
Mm-hmm.
This is 1, that's 1, this is 1. That is less than 1. What is that length? We're going to talk about that here in just a second. I'll go to the next page. Before I do, I'm kind of saying the same thing here. Now, keep in mind, though, you might have noticed it before, this width of that square and the length of the not square rectangle, those are the same
Right,
distance.
right.
Obviously, the width is not the same. Okay,
Oh,
width is not the
it's
same.
not the same?
The
It
width of
looks-
this
Oh,
green,
the width is not the same.
yeah,
The
and
length is the same.
the length is the same.
Okay.
Yes. Okay, let's go on. And here I'm basically saying that again, and you can read that. You can pause it if you're watching online and check that out. All righty. So, and here it looks like, oh, maybe the large rectangle is 2.5. We can't say that. We can't say it's 2.5 just by looking at that. It might be exactly 2.5, but we don't know. Let's go on. Now, now's a good time to say it again. The length of the large of the not square rectangle is not 3, and also the length of the large square is not 3. Okay, there's that. What is the length of the largest distributive tile? What is it from here to here? And I usually have very little trouble with students saying, we don't know. And I say, you're right, we don't know. Mm-hmm. And so the answer is D right there. Right. And if we don't know, I ask them, what do we put? And they say, we use X. Mm-hmm. Question mark sometimes, but as we go on, we've learned to use X. Mm-hmm. So there it is. There's X there. This width is a 1. This width is a 1 up here. The width of each one of those 1. Length of 1 or width, whatever. But here, this is a square, so that is X also. This is X. Now, there's that basically the same thing. We use the small square as oftentimes we call it a unit square because it has a length and width of 1. We can measure the others off of that. Mm-hmm. And the length of the large square is X, width of the large square is X. And there's that, the length of the not square rectangle is X, the width is 1. And we like to name these things by their area. So, of course, the area of the small square is now 1. 1 here, 1 there. Multiply length times width, 1. Mm-hmm. X here, multiply X times X, you get X squared. 1 here, X here, length times width, X. Length times width, X. So the name of each is its area. We can still call it a unit square, but oftentimes, because we want to know the total area, I like to call it a 1 square. I like to call this an X squared piece. And here's an X piece. And that gives us the total area. The total area shown right there is X squared plus 2X plus 1. That's the total area. Now, I wouldn't call the area by saying, oh, the unit square, the large square, and the not square rectangle. I wouldn't describe the area that way. So, again, I would say 1 plus 2x plus x squared. That's the area. And the commutative property, I said it in reverse. But here we go. Let's go to the next page. So here's the diagram I showed at the very beginning of the lesson. And now we can count. There's 6x squareds here, the blue, 6x squared, so it's either this one or this one. There's 12 of these green, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 6x squared plus 12x's plus...
6 of the little square.
And 6 ones.
1.
Yeah, 6 times 1. That's a 1, that's a 1, that's a 1, that's a 1, that's a 1. So it's B. There's the answer B. Okay, let's go on. And now, which is best organized? And someone might think this is because, it looks like it's neater. It's, it doesn't have so much white space in between.
Right. That's what I thought at first.
Yeah.
But actually, it's A, isn't it? Because
Yeah.
you've got them grouped.
Right. See, this one's got the X's kind of some here, some down here, some here, some on the other side. So they're not well organized. The same thing here. The X's are kind of scattered all over. The unit squares are kind of scattered all over. But here, everything is organized. Well, it's the best organized. Yes, the best organization you get. So there's A. And when all 24 pieces are arranged into one big rectangle, what is the length of that rectangle? Well, from here to here, it's X. From here to here, X. Here to here, X. Here to here, 1. Here to here, 1. Here to here, 1. So that's X plus X plus X plus 1, 2, 3, plus 3. X plus 3 right there. X plus 1 plus 1 plus 1, I meant to say. Or 3X plus 3 down here on this side. And so there it is.
That's probably D.
D right there. 3X plus 3. Looking down this way, maybe I can say it better this time. X plus 1 plus 1. That's 2X plus 2. Right there it is, and that's A. And here's another way that you could draw it much easier on your paper. Sketch it out like that. Sketch it out like that.
3X plus 3, that makes sense.
Yeah, for the length, and 2X plus 2 for the width. Okay, so let's go on. And there's kind of repeat. And so there's your trinomial. And going back just one, you can see these are the factors. The factors are numbers you multiply, in this case, to get the area. So the numbers you multiply, there's two numbers, 3X plus 3 multiplied by this number, 2X plus 2. When you multiply those two together with a FOIL, you get 6X squared plus 12X plus 6. So the factors of 6X squared plus 12X plus 6 are those two numbers, sort of like saying the factors of something like 12, you could say are 3 and 4. Well, there's other factors, 6 and 2, but that's the idea. Let's go on. So, the FOIL, remember, 3X times 2X gives you 6X squared. That's the first. But FOIL, O is outside, 3X times the 2, the outside terms. That's 6X. Then I is the inside terms. 3 times 2X, that's 6X. So you got two 6X's. That's 12X. And then the last terms, 3 times the 2, and that's 6. Let's go on. And there is another problem. I'm going to let you study that. And you can see the answer there is C. You can pause it and look at it. There's that. You can pause it, look at it, and see that the answer is D. There's another problem. Okay. And here's one. What's the total area of the distributive tiles? I have time to do this one. I guess. I mean, you've got 2x squared. A little harder to do. You got to multiply. 2x squared plus, you got to factor it. I'm sorry. 2x squared plus, what's that? 5x plus 4. And you factor it like I showed you back over here. Factor it, put it all together in a nice diagram, and you can factor it. And you'll see what it is there. All right, that's the end. Hope this helped. If you have any questions, probably ask in the comments where someone smarter than I will be able to help. So a lot of people are going to be able to help you, I think. Also, if you find any mistakes, please let me know in the comments, and I will try to fix them as soon as possible. Do you have any questions there, Riaz, before I close this?
No, I think I understand it actually fairly well. You've
All right.
simplified things.
And I was actually trying to say this funny, but that didn't come out too well. But good enough. I'm going to stop this video. Have a good day. Hope you learned from it.